Hello everyone, I welcome all of you in next last lecture of heat and mass transfer subject. So this is your 8th lecture of heat and mass transfer. So before I start this class, I'd like to revise the topics which we discussed already in our previous classes. So previously we had discussions on heat, temperature, units of heat, units of temperature, modes of heat transfer, conduction, convection, radiation. In conductions we follow Fourier's law of heat conduction. In convection we follow Newton's law of cooling. In radiation we follow Stephen Boltzmann law, and then we discussed about general heat conduction equation of uh, slab or Cartesian coordinate or comma cylindrical body and spherical coordinate. So this all we discussed in our previous classes, or we also followed amount of heat transfer through slab, amount of heat transfer through cylinder, amount of heat transfer through sphere without heat generation, steady state and one dimension. And at the same time, so we got the formula Q equals to K into A T1 minus T2 by L for slab. For cylinder, Q equals to 2 pi KL into T1 minus T2 by ln of R2 by R1. And for sphere, Q equals to 4 pi K R1 R2 into T1 minus T2 by R2 minus R1. So, and in the next class, in next we have seen the composite slab. So amount of heat transfer through composite slab means Q equals to A into Ti minus T naught by 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. And overall heat transfer coefficient we have seen U equals to 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. So up to this we completed. Now going forward, today we will discuss on amount of heat transfer through composite cylinder. Now yesterday we discussed on composite slab, so today we'll start from composite cylinder. Okay, so let's start then. So you see heat flow through composite cylinder. Here we can first see the diagram. So first you try to visualize this diagram. So you see here cylinders are there. So you see how many cylinders is there? Only two cylinders. You see first one cylinder is there, which has inner radius R1 and which has outer radius R2. So this is the first cylinder, and in the second cylinder you can see in the second cylinder it has also the inner radius R2 and the outer radius R3. So this is my second cylinder. Okay. So if I ask you to tell me the thickness of the first cylinder, so what is the thickness of the first cylinder? That is R2 minus R1. And what is the thickness of the second cylinder? That is R3 minus R2. So R3 is the outer radius, R2 is the inner radius. So thickness of the second cylinder is R3 minus R2. Next, we have taken that the length of the cylinder is L, and now you take same condition that inside of the first cylinder there is air, or air is present, and outside of the cylinder, second cylinder, air is present. So inside air is there and outside air is there. So if you try to analyze the picture right now, so what you have, inside of the first cylinder there is air, and then we have one first cylinder which has inner radius R1 and outer radius R2. Then we have second cylinder layer which have inner radius R2 and outer radius R3. And then we have outside air, and we have the length of cylinder how much? L, and we have temperature of the inside air is Ti, temperature at R1 radius is T1, temperature at R2 radius is T2, and temperature at R3 radius is T3, and at the outside temperature is how much? T0. So you can see here there are two cylinders from inside. Inner radius of the first cylinder is R1, outer radius of the first cylinder R2, inner radius of the second cylinder is R2, and outer radius of the second cylinder is R3. So inside of the first cylinder there is air, and outside or beyond the second cylinder air is present. So inside air temperature is Ti. Temperature at R1, R2 and R3 are T1, T2 and T3, and outside air temperature is T naught or TO. Now you see here heat will flow from where to where. So for this you try to take the one assumption that Ti is more than T1 is more than T2 is more than T3 is more than T naught. So generally the heat will flow from high to low gradient. So here also high is Ty and low is T naught. So heat will flow from inside to outside, means from Ti to T naught direction. So you see heat flows from inside air to the first cylinder. So this is the first heat flow. And then in the second time the heat will flow from the first cylinder. That means through the first cylinder heat flows. And then in the third time heat flows from the second cylinder or through second cylinder, and in the last time heat flows from second cylinder to the outside air. So this is the heat flow. Now we'll take one by one. So heat flows from inside air to the first cylinder. So means from Ti to T1. Now tell me, what is the mode of heat transfer then? It is a convection mode. So in convection mode, the formula of heat transfer Q1 equals to Hi into A1 Ti minus T1. So what is this Hi? It is convective heat transfer coefficient inside. And Ti minus T1 we can write Q1 divided by Hi into A1. In the next time heat flows through first cylinder. So through first cylinder means T1 to T2. Now this one is a solid body. So solid means conduction mode. Now you tell me, in conduction mode the amount of heat transferred through cylinder. What is the formula? Yes, 2 pi KL T1 minus T2 by ln of R2 by R1. So as per the nomenclatures, if I put the value, so Q2 will be equals to 2 pi K1 into L into T1 minus T2 divided by ln of R2 by R1. So here K1 is the thermal conductivity of the first cylinder, and we can write T1 minus T2 equals to Q2 into ln of R2 by R1 by 2 pi K1L. In the second time, in the third time, again heat continues to flow through first cylinder to second cylinder. Means through the second cylinder heat will flow. Now here Q2 will become 2 pi K2 into L T2 minus T3 by ln of R3 by R2. Okay. So here what is this K2? Thermal conductivity of the second cylinder. So we can write T2 minus T3 equals to Q3 into ln of R3 by R2 divided by 2 pi K2L. So next or last heat will flow from the second cylinder to the ambient air. So means from T3 to T0. Now here the mode of heat transfer is convection, and in convection mode the formula is Newton's law of cooling, Q equals to HA delta T. So if I put the value as per nomenclature, it comes Q4 equals to H naught. H naught is convective heat transfer coefficient outside. A2 is the area at the at outside or at the outside cylinder, and T3 minus T naught. So T3 minus T naught comes Q4 divided by H naught into A2. So again you see here total potential difference is from Ti to T naught. So we have to add up all these potentials. So it comes Ti minus T1 plus Ti minus T naught plus T1 minus T2 plus T3 minus T4 equals to, we get here Q1 divided by HI1 plus Q2 into ln of R2 by R1 by 2 pi K1L plus Q3 ln of R3 by R2 by 2 pi K2L plus Q4 by H0 A2. So here also again we take the same thing, that amount of heat transfer remains same, because whatever the heat transfer occurs from inside to the first wall, through first wall also same heat will be transferred, or from the second wall to the ambient air also same heat will be transferred. So overall heat transfer remains same. So that's why I can replace the value of Q1, Q2, Q3 and Q4 with Q. So finally we get Ti minus T naught equals to Q into within bracket 1 by Hi A1 plus ln of R2 by R1 divided by 2 pi K1L plus ln of R3 by R2 by 2 pi K2L plus 1 by H naught A2. So finally we get the value of Q equals to Ti minus T naught divided by 1 by Hi A1 plus ln of R2 by R1 by 2 pi K1L plus ln of R3 by R2 by 2 pi K2L plus 1 by H naught A2. So this is the amount of heat transferred through the composite cylinder. Now here also you see you have taken or you have combined the thermal conductivity and convectivity transfer coefficient. So here also you will be needing the overall heat transfer or overall heat transfer coefficient concept. Now in this case or in this cylinder case we have to change the concept a little bit. Why? Because you see in slab the area of the each or composite slab means area of each and every slabs were same. But in the cylinder area of each and every cylinders, can you say it is same? Wow, no, you can't say it's same. Why? Because area means what is the area of cylinder? 2 pi r into L, right? 2 pi r into L. Now you see for the first cylinder the area of the cylinder is 2 pi r1 into L, and for the last one area of the last cylinder is 2 pi r3 into L. So see r1 and the r3 means inner radius and outer radius, these both values are not same, that's why area of each cylinders are not same. If area of each cylinders are not same, then you can't take overall heat transfer coefficient concept. So that's why you have to take the concept of overall heat transfer coefficient either based on inside or based on outside. So there is the small change or modifications we do for cylinder or for sphere. So you see overall heat transfer coefficient based on inside we have taken UI watt per meter square Kelvin. So overall heat transfer coefficient based on outside is U naught watt per meter square Kelvin. As area in each cylinders are not same due to difference in radius, the U concept is replaced with either UI or U naught. Okay. So overall heat transfer coefficient, if I calculate based on inside, then we can write the value of overall heat transfer how much? Q equals to UI based on inside multiply with which area you take. We have to take the inside area means A1 multiply with, now potential difference will be same Ti minus T naught or Ti minus T1. Yes, it will be same as Ti minus T naught means overall potential difference is Ti minus T naught. Only the change you are doing here, U in place of U, you take this value of Ui. So finally we get Ui into A1 Ti minus T naught. Now if you relate these two equations, then we can write Ui into A1 Ti minus T naught equals to Ti minus T naught by 1 by Hi A1 plus ln of R2 by R1 by 2 pi K1L plus ln of R3 by R2 by 2 pi K2L plus 1 by H naught A2. So we know the value of area of inside, so 2 pi r1L, and for outside the area is 2 pi r2L, so 2 pi r3L. So Ui A1 equals to 1 by Hi A1 plus ln of R2 by R1 by 2 pi K1L plus ln of R3 by R2 by 2 pi K2L plus 1 by H naught A2. So finally we get Ui equals to 1 by A1. We take this A1 from left hand side to right hand side, so it's divided. So 1 by A1 into 1 by Hi A1 plus ln of R2 by R1 plus ln of R3 by R2 plus 2 pi K2L plus 1 by H naught A2. Now you take this Ui for value equals to, so if you take this A1 in the inside of the bracket, so we get here 1 by A1 by Hi A1 plus A1 into ln of R2 by R1 by 2 pi K1L plus A1 into ln of R3 by R2 by 2 pi K2L plus A1 by H naught A2. Now we know the value of A1 how much? 2 pi r1l, and A2 means outside area 2 pi r3l. So if I put the values, then what you get? Ui equals to A1 cancel, so it comes 1 by hi plus 2 pi r1l ln of r2 by r1 by 2 pi k1l plus 2 pi r1l into ln of r3 by r2 by 2 pi k2l plus 2 pi r1l uh, by h naught 2 pi r3l. So finally, after cancellation of all the terms, we get 1 by ui equals to 1 by hi plus r1 into ln of r2 by r1 by 2 k1 plus r1 into ln of r3 by r2 by k2 plus r1 by r3 into h naught. So this is the value of overall heat transfer coefficient based on inside. Now in the second concept, we'll take this overall heat transfer coefficient based on outside. So based on either outside or inside, we can take anything or anyone. So now we'll try the same thing based on outside. So what is the formula of overall heat transfer based on outside? So Q equals to U naught into, now area will become multiply with area outside. So what is the area outside? A2 multiply Ti minus T naught. Overall heat transfer is Ti minus T naught. So based on outside, if I again relate these equations along with the overall heat transfer of composite cylinder, so it comes u naught into a2 into ti minus t naught equals to ti minus t naught by 1 by hi a1 plus ln of r2 by r1 by 2 by k1 l plus ln of r3 by r2 by 2 by k2 l plus 1 by h naught a2. Now here also I put the value of a1 is 2 pi r1l and a2 is 2 pi r3l, and from both sides I can cancel this ti minus t naught term and take this a2 from left hand side to the right hand side and put it inside the bracket. So we get finally, and replace the value of a1 and a2 with r1 and r3. So then we get here u naught equals to 1 by r1 by r3 by r1 into h1 plus r3 into ln of r3 by r2 divided by k1 plus r3 into ln of r2 by r1 divided by k2 plus 1 by h naught. So this is the value of overall heat transfer coefficient based on outside. So here I would like to finish the class. Yes. So before I end this class, I'd like to say that today we discussed on overall heat transfer through composite cylinder. In a single cylinder, we know the formula of heat transfer is 2 pi KL T1 minus T2 by ln of R2 by R1. But if we take composite cylinder, then the formula becomes Q equals to T1 Ti minus T naught by 1 by Hi A1 plus ln of R2 by R1 by 2 pi K1L plus ln of R3 by R2 by 2 pi K2L plus 1 by H naught A2. And if you take overall heat transfer coefficient concept, then you can't take the value of U here because area of each and every cylinder, means composite cylinders, are not same because of the difference in radius. So that's why we have to take the overall heat transfer coefficient concept based on either inside or outside. So here we get the value of Ui equals to 1 by Hi plus R1 into ln of R2 by R1 plus divided by K1 plus R1 into ln of R3 by R2 by K2 plus R1 by R3 into H naught. And same way we get the overall heat transfer coefficient based on outside, U naught equals to 1 by R3 by R1 into Hi plus R3 ln of R2 by R1 by K1 plus R3 into ln of R3 by R2 by K2 plus 1 by H naught. So this is it. Okay, thank you.